In the previous lecture, we discussed about the quarter wave transformer and its use in impedance matching. And in particular, we looked at the quarter wave transformer and its ability to do this impedance matching over a range of frequencies. In other words, we saw what was the frequency response of the quarter wave transformer. So ultimately, what we saw was that there exists a single frequency or distinct sets of frequencies where the reflection coefficient that is offered by the quarter wave transformer essentially becomes zero. So what we saw was something like this. So what we did, we took the x-axis as f by f0 or the normalized frequency, and the y-axis was the magnitude of the reflection coefficient gamma. So we saw that it looks something like this. And so on. So this was where f by f0 is 1. We saw that this behavior sort of repeats every odd multiple of f by f0. That is, if there is a minima at 1, there will be a minima at 3 also. So the maxima that is offered in the mod gamma, that depends on what is the normalized load impedance, that is small z, which we defined as ZL by Z0. So what we saw was essentially, as the value of ZL goes further and further away from Z0, either higher or lower, it does not matter, then this increases. So we essentially saw something like this. While the minima point does not change, the maxima indeed changes. So something of this kind. So this is as ZL goes further away from Z0. So in other words, what we saw was that as the value of small z comes closer and closer to 1, that is, the load impedance becomes closer in value to the characteristic impedance, the maxima essentially comes down, and what it indicates is that the QWT is able to provide a better impedance matching. But what we concluded was that without the loss of generality, because it has only one minima and the mod gamma sort of rapidly increases as we move further away from f by f0, or this minima, or the f by f0 sort of moves more and more away from 1 either way, the mod gamma essentially starts rising very sharply. So effectively what we concluded was that this is a narrow band transformer. So narrow band means the bandwidth over which the mod gamma is sufficiently low, that is rather small. So now let us try to define the bandwidth, or what we call as the matching bandwidth. That is, we define the matching bandwidth as the range of frequencies or the frequency range over which the QWT is able to provide mod gamma that is below a certain acceptable value. Just like when we talk of filters, the bandwidth of a filter or the bandwidth of an amplifier, there is a specific definition of that bandwidth. Just like how we say what is the range of frequencies over which the passband gain is 3 dB below the maximum gain, that is the bandwidth. Likewise, we define matching bandwidth also as the frequency range over which the mod gamma given by the QWT or the impedance transformer is below a certain limit. So the certain limit is something that we can decide. So there may be applications where this limit has to be very, very low. There are applications where the limit can be very high. So let us say for active circuits, if we say that the limit can be on the higher side, but for passive circuits, antennas, the limit can be little low. So whatever the limit is, let us call that as the maximum acceptable value of gamma, or something like gamma suffix m. This is what we call as maximum acceptable value of mod gamma. So therefore, let us redraw this figure, that is the frequency response of the QWT, and plot it as a function of the electrical length rather than the frequency. There is not much change. As we know, the electrical length theta is beta L, which is 2 pi by lambda times lambda 0 by 4 if it is fixed. So in terms of frequency, what we saw was this is defined as pi f by 2f0. So if the normalized frequency is f by f0, then multiplying that normalized frequency by pi by 2 is essentially what theta is. So therefore, whether we are plotting the mod gamma as a function of the normalized frequency or as a function of theta, the nature of the graph will not change because it is merely a linear scaling. So therefore, again, it will look something of this kind. So when the scale on the x-axis was f by f0, the minima would occur when the f by f0 was 1. But in the theta scale, when f by f0 becomes 1, theta will become pi by 2. So therefore, the minima point is when it is pi by 2. Right? Now, let us say we define that maximum acceptable gamma value or gamma m as this particular level. And we say that essentially this is the range of frequencies which I am interested in. So effectively what we want, we have to look at the range of frequency or the range of theta over which the mod gamma is below gamma m. So this is the region of interest. Why? This is because mod gamma is below gamma m. This is the bandwidth. So let us say this point, the first point where the mod gamma crosses gamma m and goes down, let us call this as some theta m. What we have seen is that this graph is rather symmetric around this minimum. So therefore, whatever is the distance from the minima on the left to theta m, the same will be the distance on the right hand side also. So what would that be? This difference is pi by 2 minus theta m. So this exact same difference has to be added to this pi by 2, and this point would then be pi by 2 plus pi by 2 minus theta m, which is pi minus theta m. So therefore, in terms of theta, the bandwidth or the range of electrical lengths, or what we call as delta theta, that is equivalent to the matching bandwidth. That is this range. How much is that? That is nothing but pi minus 2 theta m. So having said this, let us go back to the equation for mod gamma, what we had derived in the previous lecture. So we had essentially derived that for the quarter wave transformer, the mod gamma looks something like this without normalization of impedances. This is what we had derived. So let us now rewrite this expression. I'm just going to do a little bit of manipulation to remove this square root term. So mod gamma square will be ZL minus Z0, the whole square, divided by ZL plus Z0, the whole square, plus 4Z0 ZL tan square theta. Now, for ease in handling this right hand side operation, I'm just going to invert this. So let's invert this equation. So this becomes 1 by mod gamma square, that is this quantity ZL plus Z0 whole square plus 4Z0 ZL tan square theta divided by ZL minus Z0 the whole square. Now what I can do is I can just use a simple algebraic manipulation and rewrite this term ZL plus Z0 the whole square in terms of ZL minus Z0 the whole square. So I can say over here ZL plus Z0 the whole square is nothing but ZL minus Z0 the whole square, but with a plus 4 Z0 ZL term. So therefore let's rewrite this. So this becomes ZL minus Z0 the whole square plus 4 Z0 ZL plus 4 Z0 ZL tan square theta divided by ZL minus Z0 the whole square. Now what's going to happen is I can split this, and if I now keep these two separately, then I'm going to get 1 plus, if I take this 4 Z0 ZL common, I will get in the bracket 1 plus tan square theta, which is nothing but sec square theta. So this will be 4 Z0 ZL sec square theta divided by ZL minus Z0 the whole square. So having established this, let us now go back to this graph and consider the points of interest. That is this point and this point. Because those are the points where the mod gamma actually becomes mod of gamma m. There should be a mod sign over here. Right? So now, if we consider either of these 2 points where the passband actually starts or ends, then gamma becomes equal to gamma m. So therefore I can say at the passband, endpoints, I can say gamma becomes equal to gamma m, or mod gamma becomes equal to mod gamma m. So therefore, if I substitute gamma equals gamma m in the equation that we derived, that is the one before here. So the first point, let us choose the lower bound of the passband, that is when theta becomes equal to theta m. So consider theta equals theta m. In that case, the equation will become like this: 1 by mod gamma m square equals 1 plus 4z0zl sec square theta m, because it is at this point, divided by zl minus z0 the whole square. So if we just do some manipulation and try to isolate this theta m, what we will get is something like this. So I will just take the 1 over here. So I will get sec square theta m is equal to times zl minus z0 the whole square divided by 4z0zl. So let's take the reciprocal to get the cos term. So that means cos square theta m will be 4z0zl divided by zl minus z0 the whole square. So I will just quickly do the cross multiplication, and what we will get is mod gamma m square divided by 1 minus mod gamma m square. So let us take the root. That means cos theta m. Now this will be, this upper term is a positive term, so therefore the root will be 2 root z0 zl. We are going for the positive root because the cos term has to be such that its value should be positive, because theta m is below pi by 2. Now zl minus z0 the whole square, the root will be when the square term will go, but zl can be anything, z0 can be anything. I mean, zl can be more than z0, zl can be less than z0, even though they both are real in this case. So therefore, to maintain the positive sign of the cos term, we will put a mod over here. And this term is anyway positive, so therefore this will be gamma m, the root of this, divided by root of 1 minus mod gamma m square. So this is cos theta m. So therefore theta m will be what? Theta m will be cos inverse of the entire term that we just derived. This is theta m. So we have got the first point. We have got the first point where the mod gamma sort of goes below gamma m, right? So we had derived that theta is nothing but pi f by 2f0. So therefore, what we are interested ultimately is in the bandwidth. So therefore, theta m must correspond to some fm. That is the first frequency where the mod gamma goes below gamma m. So that means theta m is pi fm by 2f0. So from here we get fm is nothing but 2f0 theta m divided by pi, where f0 is the minimum frequency. So therefore, in terms of frequency, when we are plotting the absolute frequency, the minima happens at f0, something like this. So if this is gamma m or mod gamma m, this point is fm. So therefore, the net bandwidth is essentially twice this difference. So therefore, I can say the actual bandwidth or the matching bandwidth, which is delta f, that will be this difference, which is f0 minus fm and twice of it. f0 minus fm, twice of it, because this entire thing is delta f. So we have this, and all we have to do now is substitute theta m over here and just get what the bandwidth is. That is twice f0 minus 2f0 by pi cos inverse 2 times root of z0 zl divided by zl minus z0 mod times mod gamma m divided by 1 minus mod gamma m square. So we can actually take this f0 common. So we also define one more term called as fractional bandwidth, which is nothing but delta f divided by f0, normalized with respect to f0. So I can simply take f0 common and bring it over here. So this will be 2 times 1 minus 2 by pi cos inverse of this entire term. I'm not going to write it again. And many places also define something called as percentage bandwidth, which is nothing but the fractional bandwidth multiplied by 100. So this is how you can calculate the bandwidth of a quarter wave transformer. Now, all said and done, we saw that the quarter wave transformer is something that is very useful to match a lossless transmission line with a load that is purely real. So quarter wave transformer is useless for reactive loads or complex loads. QWT is used to match only real loads or purely resistive loads. Now, while it is indeed a very useful thing, we saw that there is a constraint. That is, it is a very narrow band matching transformer. That means it is able to provide you low value of mod gamma only when you are at F0 or some place which is very close, or frequencies which are very close to F0. So therefore, for applications where you need broad frequency ranges, this is a problem. The QWT is perfect when you are looking at a very small band of frequencies. When you are looking at a very small band of frequencies where, let us say, a single carrier frequency is being transmitted and the signal is a very, very narrow band signal, and you need a circuit to match, let us say, an antenna with a transmission line. So in that case, it might be something very useful. But there are receivers, there are transmitters which often may need to transmit at different frequencies. So therefore, their operation is over a number of frequencies which may not be so close to each other. So for those kind of applications where the matching bandwidth that is required is rather large, the quarter wave transformer is not sufficient. So therefore, we must ask ourselves another question. Is there any way with which we can improve the matching bandwidth of the QWT? Can the matching bandwidth of the QWT be improved? Well, that's a question which has been asked by many classical scientists over the ages. So let us then look at the QWT or relook at the QWT and try to figure out what is or what are those parts or what are the characteristics which control the bandwidth. So if you say, let us say there is this main transmission line which needs to be matched. This impedance is Z0. So I have a QWT. Let us say this is Z1. And the load impedance is ZL. So when we were doing a transient analysis of the quarter wave transformer, we had assumed that let this length be lambda by 4. But now let us assume that the electrical length of this matching section is some theta without losing generality. So we had defined that if a wave is starting to flow from here, then the first reflection coefficient it will undergo is at the boundary of these two lines, and that is gamma 0. And the reflection at the load, the reflection coefficient at the load is some gamma L. Now once the reflected wave comes back and comes to this junction again, the reflection coefficient over here is gamma 1, and we proved this earlier that gamma 0 and gamma 1 are just negatives of each other. So if you recall, we had derived an expression for gamma that is looking into this point. into the transformer. So it looked something of this kind. This was gamma 0 minus, there were some transmission coefficients also. So this was called T0, which is going over here. This was T1 while coming back, and like that. So this looks something like this: T1, T0, gamma L plus T1, T0, gamma 1, gamma L square minus, and so on. So you had a positive, negative alternately. This is for the QWT. But if I were to now extend this for this matching transformer where the electrical length is some arbitrary theta, how would this expression change? So for any arbitrary theta, how would this change? This would change with the sign. If you notice, this sign came because of the 180-degree phase shift this wave is undergoing every time it makes a round trip through this QWT or the matching section. So earlier, for QWT, theta becomes pi by 2. So therefore, the phase change undergone is pi by 2 plus pi by 2, which is pi. So therefore, if I write e raised to minus j pi as my phase constant term, that is minus 1. And that is why we get the minus 1 over here. So therefore, the point is, we have to now ensure, or rather replace this with the electrical length equivalent to one round trip. So we will say round trip, or one round trip, is effectively equal to a phase change of 2 theta, because theta going and theta coming. So therefore, the gamma will become something like this: gamma 0 plus, now the minus sign will be incorporated in the exponential. This is the round trip phase due to the first reflected wave, plus T1, T0, gamma 1, gamma L square times e raised to minus j4 theta plus so on. This is the only change. So what we are seeing is that, again, just like the previous case, the previous equation for the QWT, this is also a geometric progression. So therefore, we can write it this way: gamma 0 plus T1, T0, gamma L e raised to minus j2 theta as common, and the summation will be over n equal to 0 to infinity gamma 1 gamma L e raised to minus j2 theta the whole raised to n. This is what it's going to look like. So once again, this quantity mod of gamma 1 gamma L is always below 1. So we can very easily sum up the geometric progression in the following manner. Something like this. So in our previous analysis, you can very quickly go back and refer to them. We had shown that T0 is actually 1 plus gamma 0 and T1 is 1 plus gamma 1, or 1 minus gamma 0, whichever way you want to write. So therefore, if you substitute over here, effectively gamma simplifies to something like this. Gamma 0 plus gamma L e raised to minus j2 theta divided by 1 plus gamma 0 gamma L e raised to minus j2 theta. You can also substitute gamma 1 is minus gamma 0. So, and you can then get it. You can see very easily that minus gamma 1 would become plus gamma 0. So, the exact solution, I mean, it's not too difficult from this step. Just have to substitute. So, this is what we get. Now, we need to introspect a little bit more closely. This is a very unremarkable equation. This is a very unremarkable equation. But as engineers, our job is not just to focus on the theory, but to make some minor changes or approximations in the theory to suit our needs. Now, let us look at the denominator. What can we say? We can say from here that gamma 0 and gamma L, their magnitudes are both less than 1. Gamma 0 and gamma L, their magnitudes are both less than 1. So, if we were to multiply these two quantities, that is to get the denominator, as it is if gamma 0 and gamma L are less than 1 and we multiply the two, the product will be even more less than 1. So now this sort of gives rise to something very interesting. If the magnitudes of gamma 0 and gamma L are very less, so let's suppose we do something. We are able to keep mod gamma 0 and mod gamma L very, very less than 1, far away from 1. Then what this means is the magnitude of the product of these two will be negligible. So therefore, if we can ensure that gamma 0 and gamma L magnitudes are much, much below 1, we can effectively cause the denominator, the second term in the denominator, to become negligible. Thereby, the denominator should become 1. So in that case, what will gamma be? Gamma will become gamma 0 plus gamma L e raised to minus j2 theta. So this is something we have to introspect. This is certainly a lot easier. There is no denominator. It just seems to be a sum of two complex numbers. But let us try to understand what this means. Let us try to understand what this means. What we saw was this was the main line, Z0. And then we have the Z1 line, which is terminated with a load of ZL. Now notice that the gamma that we are seeing over here is expressed as a function of gamma 0 and gamma L. So if this length is theta, what is effectively happening is that gamma is becoming almost an algebraic sum of gamma 0 plus gamma L e raised to minus j2 theta. So if my point of observation is over here, this gamma 0 comes as it is, whereas this gamma L comes but along with that phase term which corresponds to one round trip for the wave to go here and come back. Phase change by one round trip. Okay, so this is what it is. But let us not forget what was the assumption. The assumption was we are keeping mod gamma 0 and mod gamma L are much below 1. What it means is we are trying our best. We are looking at each of these two reflection coefficients and we are trying to keep their magnitude small. In other words, the partial reflections that the waves undergo at each of these discontinuities or the boundaries is very small. So therefore, this gives rise to a new theory, and that is called as the theory of small reflections. Okay, so just by applying this, we can say that gamma is equal to this more simplified expression. But the question now is, how easy is it? How easy is it to ensure that gamma 0 and gamma L magnitudes will always be much less than 1? There is no guarantee. There is no guarantee. So, what makes us say that there are no guarantees? What is gamma 0? Gamma 0 is Z1 minus Z0 divided by Z1 plus Z0. And gamma L is ZL minus Z1 divided by ZL plus Z1. So effectively, once Z0 and ZL are fixed, Z1 is everything. So Z1 decides how far it is from Z0 and how far ZL is from Z1, which ultimately decides the magnitudes of gamma 0 and gamma L. So therefore, if the difference between Z1 and Z0 or ZL and Z1 is very large, then the notion of the magnitudes of gamma 0 and gamma L being much less than 1 is incorrect. So therefore, is there any way through which we can ensure that the reflection coefficients will be small no matter what the Z0 and ZL is? Is there any way to ensure that? Is there any way to ensure this? Well, we don't know. Let us look at this equation from another angle. Suppose we are able to ensure that the reflections are indeed small. That is, mod of gamma 0 and mod of gamma L are indeed much less than 1. What we have is gamma is equal to gamma 0 plus gamma L times e raised to minus j 2 theta. Let us not forget what our aim is. Let us not forget what our aim is. Our aim is to make gamma as 0. Why? Because we want to match. We want to match the impedance, the line and the load impedance. So, then let us ask ourselves, under what conditions in this equation will the gamma be equal to 0? So in this equation, gamma will be 0 when, let us take a special case, if the two conditions are satisfied. Gamma 0 is equal to gamma L, and secondly theta equals pi by 2. Because in that case gamma 0 and gamma L will be equal in magnitudes, this will become e raised to minus j pi, and what we will have is gamma 0 minus gamma L. Since both are equal, the gamma will be 0. Now this can be thought of as rather a root of this equation. But the problem still remains, what I asked earlier, and that is the assumption which is the foundation of this equation, that is the mod of gamma 0 and mod of gamma L should be much below 1. How can we ensure that? Well, we shall look at this in the next lecture. So in today's lecture, we talked about the matching bandwidth of a quarter wave transformer, and then we took the first step or a pseudo step towards investigating whether the drawback of the QWT, that is narrow matching bandwidth, whether this drawback can be overcome by any means, that is, can we improve the bandwidth of the QWT, and thereby we are trying to establish something called as the theory of small reflections. We shall pause at this point and we shall continue in the next lecture.